So okay, so we want to finish the trace anomaly today, do much of the chiral anomaly, and see how much we can get done. We probably don't finish everything, but let's do it. Last time we were looking at scale invariance, so we had psi going to e to the minus, well, it was equal to e to the minus alpha over 2 psi prime. So we changed from psi to psi prime, and we had d psi bar equals d psi prime d psi bar prime times a Jacobian, and the Jacobian where we had calculated was e to the minus integral e to the I integral d4 x alpha of x 3 m squared over 4 pi squared, that's m to the 4th psi, plus g squared over 48 pi squared f squared. Okay, so at this stage we know there's an anomaly, and then we just this by itself is a signal of the anomaly, and we just need now to get the anomaly relation out. So let's do that. So how do you get that? So where we're headed, let's just use that blank space there to write where we're headed. So our goal is that the trace of the energy momentum tensor is no longer 0 or small. It's alpha s over 12 pi fa mu nu plus m psi bar psi. Okay, so that's where we want to get. That's not a final resting place, but that's it for this calculation. This is the fermion contribution. Okay? So here's how we do it. We're looking at the fermion contribution to the energy momentum tensor, so it's, am I using T or theta in what I was doing? T. Okay, let's go back to T. T mu nu. T mu nu for the fermion is I over 2 psi bar gamma mu d slash left and right psi. Okay. We add this with a source. So the z of h is integral d psi bar e to the I integral LQCD plus h t mu nu. Okay. Then we apply the test. So I developed the test last time. The test will be, is z h plus alpha is equal to z of h? And the answer is no, of course, but now let's see what happens when it's not. Okay. So I'm going to then convert from psi to psi prime, use that Jacobian and see what happens. So we have psi bar d slash psi is psi bar prime id slash psi minus alpha psi bar I d slash psi. Okay, right? This is our, and this, I'm sorry, yes, it's also, it's true, it's prime though. This was with psi goes to e to the minus alpha over 2 psi, and likewise for psi bar. This piece here is the trace of the energy momentum tensor. Right, if I take its trace, it's sitting up here. Oh, T mu nu, sorry. T. If I take that trace, I get psi bar d slash psi, just like we have there. Likewise, it's, if I rescale psi bar m psi, is psi bar prime m psi minus alpha. Okay. So here then we start with z of h plus alpha. This is integral d psi bar e to the I integral d for x. I'll write the piece out here, psi bar I d slash minus m psi plus h plus alpha T mu mu. Okay. Then we note that if I change this, so I keep this part the same at this moment, make this e to the I integral d for x psi bar prime I d slash minus m psi prime. So I'm just rewriting it. There then becomes a minus alpha this and a alpha that. The first one, the d slash one, cancels the alpha that's sitting right here. This one doesn't cancel that. So this turns into then plus h T mu mu plus alpha m psi bar psi. And it's primes. Okay. Then we write this as integral d psi bar times the Jacobian times the same stuff back again, e to the I dot. And that should be primes, right? Those are the primes, prime guys. Since that's a logic. So if you look at the well, let's see, maybe I need to write it out. No, we can probably do it. If you look at the last line and the first line, and you compare the terms of order alpha. So there's an alpha. So the H piece and this are all the same now. So that would be the invariance. The alpha terms are not the same. So I have alpha trace here. I've got alpha m here, and I've got the Jacobian that depends on alpha. So comparing the first and last line, we have I integral d4x alpha times t mu mu is log j. So this is, e to the log j plus I integral d for x alpha m psi bar psi. Okay. Log j is the integral d is I integral d for x alpha times 3m to the fourth over 4 pi squared plus g squared over 48 pi squared f squared. Okay, and actually that's it. Okay, so equating these now, so you equate the powers of alpha. Alpha is arbitrary. It implies that we've derived t mu mu is 3m to the fourth over 4 pi squared plus g squared over 48 pi squared f squared plus m psi bar psi. Okay, so the usual piece we get is, this is the obvious explicit breaking. This is the anomaly. And so basically, this is the standard path here. Log j tends to be the anomaly that appears in the equation. You just have to get your normalizations right. This guy we're going to drop, but I'll tell you why in a second. And if we drop that, then we get the form we're after. Okay? So, comments. All right, why do I drop that? Anyone want to take a guess? I've got this big constant sitting out in front there. What is that? Okay. It's a shift in what? Okay, it's a shift in the cosmological constant, actually. This is the renormalization of the cosmological constant, the usual infinite renormalization. It's like the zero-point energy. So remember, T mu nu. Well, when you're forming T mu nu, you tend. Well, here's the Noether's theorem expression for T mu nu. You take the variation of Lagrangian with respect to d mu phi, multiply it by d nu phi minus g mu nu times the Lagrangians. So that's how if you think about it, the T00, the Hamiltonian, is longitudinal with respect to d0 phi times d0 phi minus L. That's usual. The whole energy momentum tensor comes that way too. So if you add a constant in L, there can be a term lambda g mu nu. Okay, so, and that then is for many things we just dropped, but that's in gravity. That's the source. That's the source term for the Einstein equations. That's the cosmological constant. Okay. The T00 then is just lambda, so that's the zero-point energy. So what we have there is we have the usual divergent zero-point energy that you get. Actually, I'm a little. I have just been carrying along. I haven't thought about this before. I'm surprised it's not negative, but these are fermions. But maybe I missed the sign on it. I haven't been that careful on it. Okay. But that's what it is. You drop it because it's renormalizes the cosmological constant. Okay, so that's comment 1. Comment number 2. Okay. Number 2 is there's also, this was just the fermion part. There's a similar one with the A mu. That's the gluon field. And that then turns the overall result into T mu nu. Trace is beta of G over 2G F squared plus the sum of the masses. Okay, so and what's interesting about what we just did is that the fermion contribution is just the fermion contribution to the beta function. Which is interesting. So it came out as a positive number. The beta function is negative, but the fermion contribution is positive. Okay. Questions about that? And comment number 3 is what about doing it other ways? What if you didn't use path integral quantization? So how do you get this thing in just plain old Feynman diagrams? Okay. So in plain old Feynman diagrams, what ends up happening? There's actually two related effects. I'm going to here use dimensional regularization. Okay. And you can see some of it. The trace of the energy momentum T mu nu, the trace of the energy momentum times T. And we sort of worked out what it was before. It's 4 minus d over 4 f squared plus, it's actually 1 minus d psi bar id slash minus m psi plus m psi bar psi. Okay, so normally these two terms vanish for slightly different reasons. This one vanishes for the equations of motion. This guy vanishes because d is equal to 4. Okay. It turns out when you do loops, neither of those end up happening. The easiest one to see is the f squared piece. So if this is an operator, let's just call it x, then the Feynman diagrams that you do, so we're making, for example, let's try taking gluon matrix element of T mu mu. Okay? Yeah, that gives you the f squared term. Okay? Is that equal to 0? Okay? So if you try doing that, there's all sorts of things going on. There's lots of diagrams. But, so here's one of the diagrams. Here's another one. Plus there's diagrams that look like psi's going around, gluon's coming out, plus vacuum polarizations, things like that. We know that all those diagrams are divergent. There is really nothing that they renormalize, so it's not like there's a parameter sitting here that they renormalize. So what ends up happening is that this, for example, this one here goes like 4 minus d over 4 times, well, it's g squared over something, 1 over 4 minus d. Ends up being finite. Okay, so it's divergent, but the coefficient ends up being finite. So you end up with that's probably the easiest way to calculate the gluon's contribution is you just do those features there. And likewise, these guys turn out also to give finite stuff. You normally think the trace, the fermion piece of the trace, should vanish. You do the calculation, it ends up being finite. Okay. So in dimensional regularization, it basically comes from cancellations like this, the 4 minus d or 1 over d minus 4. In other regularizations, it's a different story. If you did Pauli-Villars, okay, so Pauli-Villars is like subtracting off a heavy mass. Okay, so it then T mu mu, if you do this consistently, would look like things. Let's take the fermions. You know, psi bar I, well, d slash minus m, maybe a term like that, and you take some heavier guy, some heavy guy. This is the Pauli-Villars guy, and you'd subtract it off. But you're subtracting off a heavy guy, so it carries a lot of energy and momentum. And so this guy is, m goes to infinity. And so the answer ends up being, when you do the loop, it's this loop here is the one that kills you in that case. You do this loop here. This goes like Pauli-Villars regulator over the Pauli-Villars regulator goes to a finite answer. So you get the same finiteness out of doing other regulators if you do them consistently. Yeah. 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 So basically, what you do when you do Pauli-Villars is you take the loop diagram that has the fermion masses in there, then you subtract off the same diagram but with a heavy mass, so that the high energy parts all cancel and you're left with something finite. You then take the heavy mass to infinity, and that's the regulator. And so it's like just taking a field with the wrong sign for the kinetic energy pieces. So all the propagators go to the negative of the other propagators with a big mass. So it's basically the substitution in the Feynman diagrams of things that look like 1 over p slash minus m. You subtract 1 over p slash minus big M. Okay. But if you do that consistently, you end up with m's in the numerator, m's in the denominator, and they just cancel out. Okay.
But at the end, there should be something depending on
No, well, in this case, it exactly cancels, plus terms like 1 over m. Right. So the what's funny about it is you end up with this with a constant piece there. Uh, it, I remember talking about decoupling. This is a piece that seems like almost like it doesn't decouple. Okay, and I'll give you another example, right? Uh, because here, as m gets very big, you get a finite piece left over. Okay, and it's also true in the following here. This is the I'm up to comment number 4. 4.
There's a piece of 1 over m, so it doesn't count. Like,
No, you then take m to infinity. Okay, and it gives nothing then. Okay. So you're just left with the finite piece. The same story happens for heavy quarks. Okay. The story with heavy quarks is the following. To trace the energy momentum tensor, you could write it in the following way. You could write it as beta over 2g f squared plus the sum over quark masses, and let's put one way out here, plus dot 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 m t bar t. Okay, the top quark mass. Okay. Well, I said I was going to integrate out the heavy quarks, and then by the decoupling theorem, I should only have effects that vanish, go into renormalization of coupling constants, or vanish in the heavy quark limit. So, can I do that? Well, so if I integrate out the heavy quark, well, we've sort of done the calculation already, but it's basically this diagram. So I'm going to do it now as a Feynman diagram. And it turns into g squared over 48 pi squared, the equivalent of f squared. So it's just like having an f squared there. So it's not okay. So what's going on? It looks like it violates decoupling. Well, what's going on is that this beta function that I should use here is, let me call it beta 6. It's the beta function for 6 quarks. After I integrate it out, T mu mu would be the beta function for 5 quarks, f squared plus no top contribution. So the top quark contribution is just going into changing the beta function. And so this is actually then an identity. If I use this with beta 6 and mt there, I get the same matrix elements as if I use it with beta 5 and no top. Okay? So it's actually a very, very subtle feature of decoupling. I like that one. Okay. Comment number 6 or 5 is we started off by saying that the proton, particle's mass, let's take the proton, it's T mu mu, proton has to be the mass of the proton. Turns actually to be u bar times u bar u. So whatever normalization convention you use for u bar u, it always equals that. Okay. But now this is proton matrix element of beta over 2g f squared plus mu u bar u plus md d bar d plus ms s bar s proton. Now this guy is rather funny. These masses are very small. In fact, you can actually calculate that this is about 40 MeV. I can't tell you how you do that right now, but that's the pion nucleon sigma term. This guy is debated. I don't know, the proton doesn't have much strange quarks in it at all, so you'd think it'd be small, but it's not necessarily there. But this guy then turns out, an estimate is something like 890 MeV. So this looks funny from our intuitive picture of the proton, that most of its mass looks like it's due to gluons, but it's not. Okay, I don't know if we want to go through. I have a hand-waving argument that explains that. We can do that or not, or we can move on. I guess unless there's a clamor, I'll just move on. Okay.
Is it best to show that?
Well, it's hand-waving, so it's going to be... All right, let's do it. I like it. It may even be true. So comment number 6. Okay. So here, this is my mental picture for why that makes sense. Let's put a lot of gluons in the vacuum. Actually, it's actually true that there's a good deal of evidence that the vacuum matrix element of F squared is not equal to 0. Okay, so but in QCD, you basically, it's a strongly interacting theory. The vacuum has a lot of virtual gluons, anyhow. Then you want to so here's my vacuum. I come along and I stick some quarks in it, and they make this little bubble in the vacuum there where they live. So they make some change in the vacuum. So some delta E is some change in the vacuum energy times the volume of that guy. Okay. So then the proton's matrix element of T mu nu proton. Well, there'd be some little delta rho V G mu nu, because that's the vacuum piece. And I'm going to stick some matter in there, rho matter. But I'm going to make it massless. So we're forgetting the masses for the moment. Okay? So the energy momentum tensor of massless stuff goes like 1, a third, a third, a third. I don't know if that makes... This is the classic radiation in general relativity. You've probably seen that there. It's traceless. Okay. So I've got G mu nu and traceless stuff. Then this is M proton delta mu 0 delta nu 0. Okay. So it tells us that by balancing this out, rho matter, the matter energy and the vacuum energy are related. And then if you look at the MP is 4 delta rho vacuum times the volume, so the vacuum stuff. By just looking at the equation, but then if you take, it's also true that if I take T mu mu is 4 delta rho times V is that's basically the gluon stuff in the vacuum. Okay, so the physical picture actually works out numerically just right. That you've got massless matter around and some background vacuum change. That the matter makes a change in the vacuum. There's some energy difference due to the vacuum, some matter stuff, but if you take the trace, it's all consistent with being the vacuum energy, even though the whole driving feature of this was the quarks and gluons, the quarks that you put in there. Okay, this actually is the bag model, the bag model of quark structure. There's a vacuum energy and massless matter. It works out just this way in that model. But the main idea is that even though the quarks are the driving piece, numerically it works out that the trace gives you numerically the vacuum energy. So I don't know. That's my picture. I got one more thing to do here on this trace anomaly. I want to do this a non-rigorous but easy okay. But it gives the right answer in one line. I mean, it's really easy. Okay, so it's worth doing. So here's an observation that's often used. If I let GA equal some A prime, okay, so I just absorbed the coupling constant into my definition of A. Okay, then D slash on psi is then d mu plus I lambda A over 2. So there's no coupling here. Okay. Likewise, when I do S mu nu, I have d mu A, let me just do it schematically, plus G A squared in F mu nu. Okay. Well, G times one of the A's goes like A prime, and this one doesn't quite work. So, but if I pull out, so if I write this as 1 over G d mu A with a G there plus G squared A, it's then 1 over G times some F mu nu prime with no couplings there either. Okay? So this is then tells us that if I write the action turns into integral d4x minus 1 over 4 G squared F prime mu nu F prime mu nu plus phi bar I d slash prime minus m psi. And the only place there's a coupling, the coupling constant appears is right there. Okay, so the rest of the theory has no coupling constant at all. Okay, fair enough? Now, to do this derivation, we're going to realize that the coupling constant depends on scale. G is G of the scale. Okay? So that if I want to see whether the action is invariant, we know that the rest of the action, we did the calculation, the rest of the action is invariant under change of scale, but G is not. So the variation of the action with respect to lambda is, well, it's the integral d4x. It's the derivative with respect to lambda of 1 over minus 4g squared, which is a function of lambda, times f prime squared. Okay? So this is then 1 over 2g cubed d by d lambda of g. D by d lambda of g is the beta function of g. And times f squared. The integration is there, of course, also. I now go back to my original scaling. So that's f prime. And the variation of the action with respect to lambda is the integral d for x beta of g over 2g f squared. So the t mu isn't 0 anymore, but it's beta over 2g f squared. Okay? So you even get exactly the right number out from this. So there must be something true about it. It's a little heuristic, but it tells you the right physics. It tells you that the theory is scale independent, but it isn't, because it depends on the scale through the couplings, and that's governed by the beta function. Okay, so that's another favorite of mine. Okay, any questions? Yeah.
I thought the beta function was lambda times d by d lambda of g.
It's often mu d by d mu, okay? But here, mu is a dimensionful parameter, and we're rescaling, let's see. So we're changing the scale of mu by an amount lambda. So the dimensionless thing would be if delta mu is delta lambda times mu, then this turns into variation with respect to lambda, delta lambda. Okay?
Okay.
Good, I got it. No, but basically, the difference is that we normally do a dimension full parameter mu. This is a dimensionless rescaling. And that's really the difference. It's still the beta function, but I've just rescaled the momentum rather than changing it by a fixed amount. Okay, so actually that will stop my my trace anomaly thing. I think I've gone through all the aspects of that are relevant. I want to do the axial anomaly also, the other anomaly. Okay. Here there are two manifestations of this. There are two places where this is important. In the standard model. There's actually, you can do more than that, but one is what's called the U1 problem. And the other is pi to gamma gamma. I'll do a little bit of each. Since we're segueing into the standard model, these are two of the features of the standard model. I'm only going to do part of the U1 problem because I need to develop the rest of the understanding first. But here's the basic of the U1 issue. If you do Noether's theorem, you actually get 9 conserved axial currents. So let's take the m goes to 0 limit for mu, md, ms. Okay. Then we know that we normally would expect an invariance, and this is going to be spontaneously broken, and some of these things are going to be Goldstone bosons. We'll find the Goldstone bosons from Noether's theorem, and there's going to be conserved axial currents, which are related to those Goldstone bosons, and there'll be 9 of them. I equals 1 up to 9. Okay, and through arguments that will, and it's just because it's a U3 symmetry, really. There's three quarks. There's all the currents, in fact, are the following. It's Ji mu is psi bar lambda I gamma mu gamma 5 psi for I is equal to 1 up to 8, and J0, the 9th one, is psi bar gamma mu gamma 5 psi. Okay, so and this is in with psi being is UDS. Okay. If you put the masses to 0 and just take the divergences, all those currents are conserved. The expectation then is that you end up with 9 Goldstone bosons. So there'd be the 3 pi's. There'd be there's 4 kaons if you're counting them. The k plus, k minus, k0, k0 bar. There's something we might call the eta, which has a mass very close to the k on 549. And what? Okay. If you look around, there is no light 9th one. So these guys are light, so they're almost Goldstone bosons. That makes sense because the masses are almost 0. The last guy, there's nothing light. There is no last one. The last one might be the eta prime, but its mass is heavier than the proton. Okay. So there's no sense that it's light. It's very heavy. And so this is the U1 problem. There's this axial U1 current that looks like it's conserved by the equations of motion up to mass terms. You can actually predict what the mass of the 9th guy should be by using this current. I'll do that for you when I do other masses. But it doesn't work. So it turns out that this guy has an anomaly in it. 0, 5 is something times f squared. I have to look to see. It's 3 alpha strong over 8 pi f dual okay, and in my normalization, f dual mu nu is epsilon mu nu alpha beta f alpha beta. Okay, Many people use a half there, but we didn't. Okay, so quickie, some quick comments about this. The path integral version in the path integral version, we take the axial symmetry, the axial U1 symmetry is psi goes to e to the minus I beta gamma 5 psi. That's the symmetry that would generate this. That's equivalent to well, let's just leave it like that. If you do this, it is LQCD goes to LQCD if the mass terms are 0. Okay, so if you do this on any of the fields, it looks like there's an invariance. The current is the one that you got out, that I wrote out before there. However, if you do integral d psi bar, you do the path integral measure is the integral d psi prime d psi bar prime times some Jacobian. The Jacobian is e to the minus 2I trace beta gamma 5 just by doing the determinant. It's the determinant of e to the I beta gamma 5 minus 2. That's where it comes from. This trace beta gamma 5 is integral d4x, sorry, x beta gamma 5 x. Fujikawa tells us to regularize that, so we do e to the minus d slash over m squared. And you do the same sort of calculation that I did for the other one. You expand that out, you use the heat kernel. Use heat kernel. And you end up with the Jacobian is e to the minus I integral d for x beta of x 3 alpha over 4 pi, alpha strong over 4 pi ff dual. Okay, which you then do the same analysis that we did before. That implies that this current J05 isn't divergent unless it's 3 alpha over 8 pi f. Okay, so this current isn't conserved. Now let's try the simplified version of the Feynman diagram analysis. Okay. So the other way of doing it is Feynman diagrams. Okay, so we take the matrix element G, 2 gluons, J5 mu, 0. Okay, that's epsilon mu 1, so 1, 2, epsilon 2 nu Now, I have to make alpha beta some matrix element mu alpha beta. The current conservation of this would be if I take the derivative of this on this guy, turns in, once I have to put my momentum in the right place, but it turns into the condition that K mu T mu alpha beta equals 0. Where K is the momentum flowing in on that line there. Okay. I don't have a, I'm not going to be able to do this. We can do one of the two things. I can do a simplified version, but I'm going to run over even with that, or I can break here and come back and do it in a little bit more coherent version. I have the notes written out, so it's up to you. Come back, do it next time? All right, let's do it next time. I'll do it right then. Otherwise, I'm just waving my hands. Okay, let's stop there. We'll see you next time. Yes?
Can I just ask a question?
Sure, you can. Yes, we do.
Can we go back up to where we talked about the U1 problem?
Yes, that's, you can ask.
So we just have, what's the SU3 cross SU3 symmetry?
Yes.
And then we have the spontaneous symmetry,
Yeah.
and we get the 9 goals on both.
Right. Yeah, actually what you really have is you have U3 cross U3 symmetry. So you can, let's make it vector and axial, or left and right, whichever you prefer. The U1, that's the vector U1. That, so you tend, we can factorize, U3 is SU3 transformations plus a U1 transformation, right? Yeah. So basically, it's a U3. A U3 transformation is e to the I alpha 0 plus alpha A lambda A. Okay. So it's these guys are traceless. Alpha 0 is not traceless, so that's the U1, and these are the traceless ones. Okay. So U3 breaks up into SU3 plus a U1. The vector U1 is just overall quark number conservation. Okay, so this is okay, so you change the phase of all the quarks by the same amount. The conserved quantity is the sum of all quarks. Okay. So that's a pretty trivial one. The SU2 is a less trivial one. Okay. And so the U1 vector there is fine. It's the U1 axial part that is the one that's giving us the problem. So it's changing the phase of all the quarks by this e to the I gamma 5 term. Okay. That's not overall conservation number. That leads to this particular current, and so there's no evidence of this symmetry. In a way, you'd say if that symmetry were to be there, then every state that you see in the spectrum should exhibit that symmetry, right? If it's not spontaneously broken, the state should exhibit the symmetry that commutes with the Hamiltonian and all that stuff. So that if I took e to the I beta gamma 5 on the proton state, I should get another state that has the opposite parity because of the gamma 5, it doesn't exist. Okay, so you then say, well, therefore it has to be spontaneously broken. Therefore you have to find a Goldstone boson associated with it. Okay, in the case of the other SU3 symmetries, you find Goldstone bosons associated with them. You don't find one associated with this. That's our U1 problem.
Now, this is also called the axial anomaly?
Yeah, this is the axial anomaly. Yes.
And then usually those currents are written in terms of the vector current and the axial current.
Right.
Okay.
Yeah, so that's right. So, yes. So this is of the 9 vector and 9 axial ones, this is the one that has the anomaly. Okay. Anything else? So what I'm going to do next, when I do the I'm doing QCD, I'll spend some time on calculating how the quark masses influence the masses of the Goldstone bosons here, and I'll calculate what the 9th one should be. Okay, you can actually show that it should be below the kaon mass. That's where it has to live below the kaon mass. You can actually calculate what it is. I've forgotten the exact number, 300 MeV or something. If it didn't have an anomaly, and then you can show the effect of the anomaly is like pushing this eta prime up to heavier mass. Okay, so that's what I'll do. But I have to develop all the other quark mass stuff first. Okay. Anybody else?
So we'll just do the Gelman-Akubo relation?
Yes, it's actually Gelman-Oakes-Renner. Gelman-Oakes-Renner is the piece. Okay, the people who did the first ones for pions and kaons. It's like Gelman-Okubo, but so for those people who know the two phrases, Gelman-Okubo is general splitting of multiplets. So if you take the protons and the rest of the SU3 multiplet or the decaplets, Gelman-Okubo is the assumption that the SU3 breaking parameter transforms like the 8th component of an octet, and then you get all these mass relations out. Okay. So equal spacing in the decaplet, Gelman-Okubo formula in general, and for the octets. Then there's a Gelman-Okubo for the pions and kaons also. However, Gelman-Oakes-Renner is a stronger one. It's basically saying the quark mass matrix perturbs those away from 0, so that if the quark masses were 0, they'd all be massless. And so we're expanding to first order in the quark masses. Then it satisfies Gelman-Okubo because the SU3 breaking does look like an octet, but it's more powerful than that. Okay, it predicts absolute masses. Okay, so that's the slight difference between them. And everybody here's been through the 714, right? Physics 714. No, it's the introduction to particle nuclear physics. Oh, you haven't?
No.
Okay, so if I say the word jets, do you know what jets are and things like that? Okay. All right. So maybe I'll have to say some of those things. Then I was going to focus on parts of the standard model that are field theoretic parts. There's a bunch of stuff that's the phenomenology of the standard model that I'm going to assume or say briefly, and then you can ask me, and I'll do like I just did here. Go through the history of it to fill you in on whatever you need. But things like jets, there's this lore about confinement and how jets are produced and all the evidence for jets. I'm not going to go through that stuff. Okay. Good.